In today's lecture, we're going to cover iterative predictions of motion for gravitational forces, and this is for Physics 2010. In this lecture, we're going to use VPython to simulate the motion of two asteroids in orbit. So, first of all, this is the equation that governs the motion that we're going to simulate today. So this is Newton's law of universal gravitation. And in this equation, the force from object 2 on object 1 or object 1 on object 2 can be written as minus g m1 m2 over r squared times r hat. G here is the gravitational constant, which is 6.673 times 10 to the minus 11 Newton meters squared per kilogram squared. M1 and M2 are the masses in question, and R is the center of mass to center of mass distance in between those two masses. Now remember that this force is attractive and points along the line connecting the masses. Via Newton's third law, the force on 1 from 2 is equal to minus the force from 2, force on 2 from 1. Okay, so they move along, or the force is along the direction connecting the masses center to center, pointing inward towards the other mass. So this is what we're going to simulate today. We're going to play around today with the motion of some asteroids. So I decided to do this for fun. This is 87 Sylvia. This is an image of 87 Sylvia, this funny looking blob here in the center. And it's the 88th largest asteroid in our asteroid belt. And it's got a mass of 1.5 times 10 to the 19th kilograms. Now this large asteroid is actually orbited by two small moons, Romulus and Remus, of course also asteroids. So Romulus orbits Sylvia in a nearly circular orbit, and it has a radius of 1,360 kilometers. Its mass is 9.3 times 10 to the 14th kilograms. Looking it up, you can find that the period of the orbit is 3.6 days, which would be about 315,000 seconds, and that gives Romulus an orbital speed of 27 meters per second. Now, as you can see in the picture, Sylvia is not really a sphere, it's actually egg-shaped. But if you were to simulate this with VPython code, maybe you want to use a sphere because it's just easy. So we can model Sylvia as a sphere with an average radius of 286 kilometers. Okay, so that's what we're going to do. Now, we're going to model the gravitational force that Sylvia exerts on Romulus and model this little orbit. And when we do this, we're going to ignore Remus, okay? But bear in mind that in VPython code, it would be not too hard to add in extra bodies and then calculate the total force. So we're going to do those kinds of things in future assignments. But let's start with something simple for today. So we'll just pretend that it's Sylvia and Romulus and that's it, okay? So if we do a simulation of the motion, we're going to use the iterative technique that's covered in chapter, I think it's chapter 2, maybe chapter 3, of matter and interactions. So this iterative technique says that while you're in a loop, which means it's going to repeat over and over again, remember iterative means repeating, that what you're going to do within the loop is calculate the net force vector, we'll call it F net here, acting on a system. And this will be a sum, of course, of all the forces acting on a particular object, okay? Then, for that object, we're going to update the momentum. So, we're going to use the momentum update equation. P final is equal to P initial plus F net times your time interval delta T. So, delta T will be defined, it's the time interval of 1 time step, okay? And then we're going to update the position. R final is equal to R initial plus V average times delta T. Now here, V average is the average velocity during that time step, and you find it by taking the momentum calculated in the middle step and dividing that by the mass. Okay? So we already talked about how to do this in a simulation with projectile motion and then one with springs, but now we're going to do another simulation using gravity. Okay? So that first step, calculate the net force vector acting on the system. Matter and interactions in chapter 3 goes through how to calculate the gravitational force in a step-by-step way. So we're going to follow this method in our code that we're going to use to model the motion of Sylvia and Romulus. So the steps for calculating the gravitational force are outlined as follows. First, you're going to calculate the displacement vector between masses, right? So here, r, for example, would be r2 minus r1. And that would give you the displacement vector between those two masses. Next, you'll calculate the magnitude of that vector, which would give you the distance between the two bodies, center of mass to center of mass. Then next, you calculate the magnitude of your gravitational force. Now notice there's no minus sign in here, okay? So here we have g times m1 times m2 divided by the magnitude of r squared. That's the next step, calculating the magnitude of the force. Next, you calculate the direction of that force by getting minus r hat. So that's the unit vector associated with the vector r from the first step multiplied times minus 1. And then you multiply the magnitude that you calculated in step 3, g m1 m2 over r squared, times the direction that you calculated in step 4 minus r hat to find the force vector, okay? So that's what we're going to do. Now, a couple of things. If you're going to enter a number in scientific notation in VPython, you use a notation similar to what you might find in Excel or maybe your calculator. Here, for example, I'm going to call the mass of Sylvia little m big S, right? That's Sylvia's mass. And remember, that was 1.5 times 10 to the 19th kilograms. And so we let e to the 19 symbolize times 10 to the 19th. And it doesn't matter if you use a capital E or a lowercase e for that. Either one will work. So we would also enter our gravitational constant this way, 6.673 e minus 11, and VPython understands that to be 6.673 times 10 to the minus 11. Okay? We're going to have to do the magnitude of r squared here. And remember, this is tricky to remember, and I apologize, but this is just how it is. If you're raising something to a power in VPython, you use two asterisks like this. You don't use the caret symbol, okay? So 5 star star 3 is 5 cubed, right? Or r star star 2, that's r squared, all right? Now, if you're going to calculate the magnitude of a vector or calculate a unit vector, here's how you would do that. If you want the magnitude of the vector, let's say that you defined a position vector and you want the magnitude of it, it would be mag of r. And that gives you the square root of the sum of the squares of the components. Of course, you could do that manually, but it's clunky, and this is a lot more elegant. You can also find a unit vector in several different ways. My favorite is the command hat, right? So if I wanted to find, let's say I have a vector r, and I want to find the unit vector associated with that vector, then r hat is equal to hat of r is one way to do it. Another quickie is norm of r, but I like hat better because I always say r hat, so it's easy to remember. And then you could also always do it manually like this, where you take the vector and divide it by its magnitude. And that's a nice way to kind of cement what the definition of a unit vector is in your head too. So all of those ways would give you the same unit vector, just so you know. Okay, so I've got Gravity Sim Rocks. That's a link to my code, and I'm going to pull that up now, and we'll go through it step by step and chat about it. So here's Gravity Sim Rocks. What I'm going to do is first I'm going to call my visual package, and that imports a lot of commands that make my life a little easier in VPython rather than having to call them individually. Now remember that before your loop, in the front matter of your code, you're supposed to define all of your variables, get all of your variables, your constants defined, and also give initial conditions to any vectors or values that you're going to update within your loop. So our constants here would be the gravitational constant big G. I've defined that here, 6.673 e to the minus 11, so that's times 10 to the minus 11. The mass of Sylvia, and then the mass of Romulus. And those are all laid out according to the information that I gave you. Remember that if you want to comment, if you want VPython to ignore something on a line, then you use the hashtag, and then after that it'll ignore anything that occurs, okay? So this is some of the text that I had within the PowerPoint presentation that you might have seen. Okay, next, let me make this a little bigger. It might be easier for y'all to see. Next, I'm going to define the initial values of the position and the momentum of my bodies. So Sylvia, yeah, I know I spelled that wrong here, but I don't want to fix it in my code, so I'm just not. So Sylvia here, I'm going to make a sphere. And I'm going to put the position of Sylvia initially at my origin. So pause equals vector 0, 0, 0. Remember, that defines the position vector for your object, which in this case is a sphere. Now, the radius of Sylvia is known as 286 kilometers, so I made the radius of my sphere 286e3 for 286 times 10 to the third meters. All right, I like to keep my units SI within my VPython code when I can. It just makes interpreting the code later a little easier. I made Sylvia green, and I turned on Make Trail so that you can see the path of Sylvia through space. Now Romulus, that's also a sphere, and I'm going to put it in the X direction, which will be on our VPython screen to the right. Okay, so plus X is to the right on our default screen here in VPython. So I'm creating a sphere, I'm putting it to the right of Sylvia by a distance of the average radius that was outlined here. Remember, it said that it travels in a nearly circular orbit with a radius of 1,360 kilometers. And so the position vector here, I'm putting it to the right at 1,360 kilometers, and then I'm putting it at y and z of 0. Okay? Now, I didn't really look up how big Romulus was. I probably could. But just so that it would be visible on the screen, I made it about a third as large as Sylvia. So it'll be a slightly smaller sphere, but still visible. And I made it red, and I turned on Make Trail. So we're going to have red Romulus orbiting green Sylvia, okay, on our screen. Now, here it says in the code that Romulus has an orbital speed of 27 meters per second, and it travels in a nearly circular orbit, okay? So if I put Romulus to the right of Sylvia, which is plus X, then if it's traveling in a circle, then that would mean that at any given point, the motion would be tangent to that circle. So if I put it to the right at plus X, then that would mean that I would need to make my velocity in a direction of y or z. Now, because the default for VPython is kind of the xy plane there, and then z would be into or out of the screen, I went ahead and gave it a y component. Oop, I was messing with it here. Let me make that 0. I gave it a y component of the velocity of 27. Okay? Now, for the momentum of Romulus, I multiplied the mass of Romulus times that initial velocity vector, which is 0, 27, 0. Okay? Now, for the momentum of Sylvia, I'm going to have it be at rest, because the way that it's described here, it says that, Sylvia is basically sitting there stationary, and Romulus is orbiting it with a speed of 27 meters per second. So I gave Sylvia an initial velocity of 0, and then, of course, to calculate the momentum, I multiplied that times the mass of Sylvia. All right, now, it tells me that my orbital period is 3.6 days, which multiplying times, 3,600 seconds times 24 hours gives me a period of about 315,000 seconds. So I wanted to see at least 2 orbits, so I more than doubled that. So let me go ahead and fix that. I was monkeying with my code. So I'm going to set my time as 630,000 seconds, and that'll take it through slightly more, or roughly 2 periods, right? So while time is less than 630,000 seconds, that should give me roughly 2 orbits, okay? Now I made my delta t 1/100th of an orbit, okay? So I like to do that. I like to start off with that as kind of as a default, and then if I need to adjust my delta t, I will from there. So whatever motion I'm looking at, I take the amount of time that motion is going to take, I divide it by 100 and make that my time step. It's just something that I usually do. You don't have to do that, okay? It's my procedure. But then if it needs refining after I run the code, I do that. So there you go. And then I initialize my clock at t is equal to 0. So that's all my front matter. Now my loop, I'm going to run for, like I said, about 2 orbits. So that's 630,000 seconds because it's 315,000 seconds per orbit. I set my rate up. Remember, the rate statement is very important in order to visualize the code. If you don't have a rate statement in, the code will run way too fast and you won't be able to watch the motion, okay? You can adjust your rate statement as needed. I gave it an initial rate of 50, which means that the loop will run 50 times in a second. Okay, now remember, here's what we're doing. We got to first, in our loop, let's go back and remind ourselves of our steps here. What we're going to do is calculate our net force vector, and then use the momentum update equation, and then use the position update equation in each step of our loop. And in order to calculate that force vector, I first must calculate R2 minus R1, then the mag of R, then the magnitude of the force, and then the direction, and then finally multiply the magnitude times the direction. So that's exactly what I'm doing here in my code, okay? So here's R. R is Sylvia.pos minus Romulus.pos. So that's the position vector there, right? R final minus R initial, basically, or R2 minus R1. Next, I'm going to calculate my, well, I can put that in here. Well, no, I won't. Okay, so here is my unit vector. Okay, so R hat is equal to R over mag of R. Now, since I have an easy time calculating the magnitude of R, I went ahead and just put it straight in my magnitude of my force equation. Okay, so remember, it's G times the mass of Sylvia times the mass of Romulus divided by magnitude of R, which is the center to center distance between Sylvia and Romulus, squared. Remember, star star for squaring. Okay? So I just went ahead and put my magnitude calculation within my calculation of the magnitude of my force. Now, once I have that, right, then what I do is I take the magnitude of my force and multiply it times negative R hat, which is the direction of the force. So the force on Sylvia would be F mag times minus R hat. Okay? So that's following those steps, right? That's outlined in how we calculate these things. Now, once I've calculated my force, I apply my momentum update equation. So the momentum of Sylvia is equal to the old momentum of Sylvia plus the force on Sylvia times delta T. And then I do my position update equation. This Sylvia's position is equal to its old position plus V average, which is Sylvia's momentum divided by its mass, times delta T. Okay? Now that was for Sylvia. Let's also let Romulus move. Okay? So, via Newton's third law, action-reaction, the force on Romulus, F on R, is minus the force on Sylvia. Okay? So that was an easy calculation, right? That's the force vector. Now I'm going to use my momentum update equation. The momentum of Romulus is equal to the old momentum of Romulus plus the force on Romulus times delta T. So that's updating my momentum. And then I've got to update my position. Romulus.pos is equal to the old value of its position, Romulus.pos, plus the average velocity, which is PR over MR, right? The momentum of Romulus divided by its mass times delta T. Okay? That's it, right? We calculated our force, we updated our momentum, we updated our position. And we did that for both Sylvia and Romulus, so that I'm allowing both of them to move here. And then increment my time, and I get out of my loop. Okay? So that's my code. Now let's run this code so that you can see it. Okay, so here we have the green big Sylvia being orbited by the little red Romulus, and it makes a nearly circular orbit. So that is exactly what I set out to simulate. Okay, force of gravity at work. Now that's a pretty simple simulation, okay, because it's just a circular orbit. And so here you're doing something that you probably could have completely figured out analytically, right? But what if things get more complicated? Then your analytical solution becomes tougher to do. But it's no problem to simulate. Like, for example, what happens if I make Romulus and Sylvia the same size? Right? What happens if I just make that one change? Okay? Well, theoretically what should happen is that now both of them are going to be orbiting the center of mass. So let's see what happens here. Let's run it. Look at that. So with just that one quick change, you can see that the motion changes a lot. Okay? Now I can do other things, right? Let's put Romulus back small again, and now let's increase our time increment, or our time limit, and let's give Romulus an initial velocity, right, and see what happens. So before, we had a velocity that was just in the y direction so that we could simulate that circular orbit, okay? But if I give it an additional motion in, say, the X, then that would give it some speed away from or towards Sylvia, right? And so let's see what happens then. Well, now see, I've got an elliptical orbit, okay? So that's a different situation. And I could make it even worse, right? I could make it even faster away from Sylvia, and we'll see what happens. Look at that, okay? So you can see that you can take this relatively simple and straightforward code, and you can change little things in the code and use it to simulate even more complicated situations than what you originally intended. And this is one of the real powers of simulation. This is what it's really for. At NASA, at SpaceX, they don't do analytical calculations by themselves anymore, right? Everything is simulated. And it's important to understand, too, that if you want to insert more bodies, like let's say that you wanted to put in Remus 2, then that would just be a few more lines of code, and now you're solving what we call a three-body problem. So in physics, there's really no generic kind of analytical solution for multi-body problems, and they must be simulated in order to see what happens, okay? And so, lots of folks have this picture in their head of the Big Bang Theory, where you have, Sheldon and Leonard standing next to a whiteboard and figuring everything else out by just writing on a whiteboard. But the reality of the situation is that in order to figure out complex problems, numerical simulations are used all the time. So instead of that mental picture, maybe switch your mental picture and show Sheldon and Leonard huddled around a computer screen coding in complicated things. Okay, so I hope you enjoyed that and learned from it. And let me know if you have any questions. And as always, I'll see you in class.